this is equal to the work done moving 1 mole of a single positive charge, such as potassium ions. They have a single positive charge on them, from in to out. This is equal to negative the membrane potential times Faraday. Where E sub m is equal to E in minus the potential on the outside. This piece here is analogous to what we saw earlier, where it looked like this, right? It's analogous, but it's for a very unique, particular situation that we're talking about only. There's still a potential difference, right? So E sub m is there's still a potential difference there. And the negative sign here comes from the fact that if we had a membrane where the extracellular space is positive and the intracellular space is negative, then moving the potassium in to out, I would expect a negative sign. And again, this is also the way this is written in your book, and the way this example is for moving only 1 mole of potassium ions, but you could move more things, and that is where your new comes in. And again, this was higher concentration. This was a lower concentration of potassium. So that's our change in free energy due to the electric potential difference. We can also calculate the change in free energy due to the concentration difference. This will be equal to the free energy sort of out minus in, final minus initial. This is, again, I'm moving out. This was just convention for setting up resting membrane potential. So this is equal to RT, the natural log of the concentration of potassium on the outside over the concentration of potassium on the inside. Okay. We had a relationship for delta G. It was equal to the integral of the difference in chemical potential integrated over the number of moles moving, right? It looked something like this before. I already told you I'm only moving one thing, 1 mole of potassium ions, and we also have a relationship for chemical potential difference related to concentration difference. There's another equation that sets that up too. So we're jumping some steps we've already gone through to get to this. Okay? So if I want the sum, total change in free energy when I move this 1 mole of potassium ions out, it's going to be just the concentration plus the electric parts. Okay? Those are the only 2 parts that we have for our electrochemical gradient. The concentration, free energy change, and the electrical potential energy change. So I can write this as RT, the natural log of the concentration of K plus on the outside, the concentration of K plus on the inside, minus the membrane potential times Faraday's constant. And so if we have no net flow of potassium ions, then this is telling us that delta G is equal to 0. We've reached equilibrium. We're only considering potassium. So if there's no net changes, sort of overall, kind of from a macroscopic perspective, delta G will be equal to 0. So this will be equal to 0. And so then I can rewrite this as RT, the natural log of, what am I doing? I skipped steps on my notes, and I want to put them back in. RT, the natural log of K plus outside, concentration on the inside would be equal to, and I'm just going to divide both sides by Faraday's constant. Okay. And so basically what this is this is equal to sort of the resting membrane potential, or equal to E sub K if the only thing contributing is potassium. Okay? So if you're asked for, or I think in the homework you're given, like, here's the membrane potential for the calcium or something, or here's the membrane potential for the sodium ions for the squid axon, and here's the membrane potential for the potassium ions for the squid axon. E sub K, E sub Na, E sub Ca, whatever it is, whatever ion you're talking about, this is the contribution or the resting potential if you were considering only that particular ion. Okay? We've only considered potassium so far. Okay? And again, this is if, if there is nothing else. If you change your ion of interest so that it's not +1, then what we're going to put in, and this is maybe a little bit confusing, but we're going to put the nu back in. So now we have, for any charged ion M, we can calculate a membrane potential for that particular ion, or a contribution to the membrane potential for that ion, equal to RT, the natural log of, this will be just the concentration on the outside. This will be just the concentration on the inside. I don't know what the charge is. It could be anything. This nu, so first of all, what was wrong on your equation sheet is there was a negative sign in this equation that shouldn't be there. So remove that. I will remove it if you haven't already. There shouldn't be a negative sign here, because what this nu encompasses now, sign and magnitude of your ion, meaning if it's Ca2+, it's a calcium. This is equal to 2+ now. If we're talking about chloride ions, this is -1 now. Okay. And this is what your book calls Nernst equation like 2.0 for a neuron membrane.